here. Welcome to today's video on scientific notation. So today what I wanted to talk about was how we use scientific notation and a little bit how it relates to what we've been referring to already in terms of sig figs and everything like that. Before we go too far into that, I just wanted to make sure we did a little bit of review on base 10 numbers, just because it's a very important part of the scientific notation. So if we recall, taking a number to an exponent means we're basically taking this base number, such as 10, to an exponent 2, meaning we are multiplying the base number 2 times. So with 10 times 2 gives us 10 multiplied by itself 2 times, which gives us 100. Note that 10 times 10 equals 100, which has 2 zeros, the same as the number of the exponent. In the case of 10 to the power of 3, we know that's 10 times 10 times 10, which of course gives us 1,000. 1,000 of course having 3 zeros. And it's important to recognize that pattern as you start to get to larger and larger numbers, that if we take a number such as 10 to the power of 5, instead of having to multiply 10 5 times or even plug it into our calculator, we know that this has to be 1 with 1, 2, 3, 4, 5 zeros after it, count back from this way to find the comma, and we know that this is equal to 100,000. The same is true for negative exponents, except this time we're taking the inverse of this number. That is, we're taking this number and we're putting it under 1. So 1 over 10 to the power of 1, or 1 over 10, which equals 0.1, or 1/10, which is just one spot past this way to the decimal. So one spot over to the right of the decimal. If we had 10 to the power of negative 3, well, it's just the inverse of 10 to the power of positive 3, which is 1 over 1,000, or 1,000th, 0, 0, 1, 1 in the 1,000th spot. And you'll notice too that this number, the 1, is 3 spaces right of the decimal. So again, the exponent rule applies that the 3 minus now, instead of it being the number of zeros, it's where the 1 is located to the right of the decimal. With 10 to the negative 1, it was located 1 to the right of the decimal. With 10 to the minus 3, the 1 is located 1, 2, and 3 to the right of the decimal. So it's just important to note, especially as we go into scientific notation, when we start multiplying numbers by base 10 numbers, what exactly it is that we're doing. So if we go, let's just open up this. So we know that in science, we talked about this a little bit before, that we know scientists deal with very large and very small numbers. So anything from the size of the universe or distance between planets to the size of wavelengths of light or the size of subatomic particles. So it's important for us to have a way to express these numbers, especially as they get increasingly large or increasingly small. Now the method that scientists use to deal with these kind of numbers is called scientific notation. Now to write a number in scientific notation, the number must first be expressed as a number between 1 and 10. This number we'll refer to as what is called the mantissa. Mantissa, that's an S, a poorly done S. So the mantissa is the actual number between 1 and 10, then we multiply it by a 10 raised to a certain power. It's important to note when we're talking about significant figures that the mantissa is the only numbers we actually count as significant figures. So for example, a number that's often used in chemistry is this number right here. And that is a number I'm not even going to begin to try to describe, but this number here is Avogadro's number. And this is the number of particles in a mole of any substance. So this large number here defines how many molecules or particles make up a mole. Now instead of having to write this number out every single time you described a mole, we simply use 6.02 times 10 to the 23 particles per mole. So this is what we call scientific notation. This 6.02 here, this is what's referred to as the mantissa. and the mantissa is the only thing that we use in terms of counting significant figures when we use scientific notation. This 10 to the 23 refers to the fact that after the decimal, we're going to move it 23 places to the right. More on that later. On the reverse way, this number here, 0.000004 meters, this is the wavelength of violet light, which instead of using all that notation there, we simply write it in scientific notation 4 times 10 to the minus 7. So let's talk about how we take these numbers. So converting from decimal notation to scientific notation. When we refer to decimal notation, we're just talking about how we would regularly write numbers. So first we want to count the number of times that you move the decimal point to produce a number between 1 and 10. So that's creating the mantissa. So let's take a look at another example that we might use in science. So the distance from the Earth to the Sun, it's taken at approximately 93 billion miles. So instead of having to write 93 billion miles every time we refer to the distance of the Earth to the Sun, what we're going to do is we're going to make this into scientific notation. So the decimal would normally be here after the 0. So what we're going to do is we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we put the decimal here, and now we've created that number that's between 1 and 10, 9.3. So there is our 9.3. And now we're going to take that and we're going to multiply it times base 10 raised to the power of the number of times we moved the decimal. So we moved it 10 times, so we're going to multiply this to the power of 10. So 9.3 times 10 to the power of 10 is the approximate is the distance from Earth to the Sun written in scientific notation. Again, if we were to see this, 9.3 times 10 to the power of 10, it's basically just saying 9.3 times, again, if we were to write this into decimal notation, we know that it's going to be 1 with 10 zeros after it. So 1 and then keep going here. And last set. So we know that this is really 9.3 times 10 billion, which is 93 billion. So scientific notation, 9.3 times 10 to the 10 miles. A lot easier and less cumbersome to write than all of this or all of this. Let's take a look at the reverse example. In this case, we're looking at the average diameter of a grain of sand, which is taken to be about 24 thousandths of an inch. So once again, let's take that decimal and let's move it to where the number would be between 1 and 10. 1, 2, 3 there, right? So that makes the number 2.4. So 2.4 is between 1 and 10, so we're going to write that out, 2.4. Now we're going to raise it to the power of 10, right? So we're going to take a base 10, and we're going to raise it to a certain power. And the power we're going to raise it is to the number of places we move the decimal. Once, twice, 3 times. Except only now, in this case, since this number was less than 1, since this number was a decimal number that we turned into a whole number, we're going to actually make this 10 to the power of -3 inches. Or again, if we were to write this in our decimal notation, in the same frame, 2.4 times 1 times 1 over 1,000. So 2.4 thousandths, which is where this line is located anyway, 2.4 thousandths. So, just to refresh, it's the number, the mantissa, times 10 to the number of decimal movements. Remember that the exponent is negative if the number is less than 1, and the exponent is positive if the number is greater than 1. Let's quickly touch on going the other way now. Let's say we have scientific notation, and we want to kind of relate this to a number that we can actually say out loud. So actually going from the condensed version into the long version, decimal notation. So the first step you would do is you'd write the mantissa and move the decimal point the number of places indicated by the exponent. So I'll just skip ahead here and just point out that if we move the decimal point to the right, the exponent is positive, and if we move the decimal to the left, the exponent is negative. So in this case, we have 2.4 times 10 to the 5. Okay. Now we have 2.4, so we're going to write that out. Okay. We know if the exponent is positive, we're going to move the decimal point to the right, and we're going to move it to the right 5 times. So once, twice, 3 times, 4 times, and 5 times, we're going to place that decimal here. In each one of these little chasms, we're going to write our 0. 1, 2, 3, and 4 zeros. So that decimal's over here now, so this number now becomes 240,000 miles. Fix that 4 up. 240,000 miles. My writing is all over the place today, but hopefully you guys can see. Move it 5 times to the right because the exponent is positive. We've turned this 2.4 times 10 to the 5 into 240,000 miles, which is a bit of a more effective way to actually communicate regular language. In this case, we're going to look at the average thickness of copy paper, which is taken to be about 5 times 10 to the minus 2 millimeters. So first step, we're going to write the mantissa. In this case, because it's just the number 5, no decimal, we just have 5. So we're going to take it from where the decimal would normally be, and since the exponent is negative, we're going to move it to the left, and we're going to move to the left 2 times. So the decimal will normally be here, so we're going to move it once to the left, we'll move it twice to the left, and I'll place our decimal right there. We'll fill the little valley here with a 0, and what we get is 0.05 millimeters, or 5/100ths of a millimeter is the average thickness of copy paper. So that's all I really want to talk about today. So just again to note, if we're going from scientific notation to decimal notation, we move the decimal to the right if the exponent is positive, we move the exponent left if the exponent is negative, and then just to reiterate here, going from scientific notation, we know that it's the same basic idea, move the decimal until we get into a number between 1 and 10, and if we have a number that's greater than 1, such as 93 billion miles, we know that it's going to be taken to the power of a positive exponent. If it's a number that's less than 1, such as 24 thousandths of an inch, we know that we're going to take it times 10 to the power of a negative exponent, like 10 to the power of negative 3. Anyway, thank you guys very much for watching. I hope you guys enjoyed. We'll see you guys on next class.